Hello out there in Calculand. Today we're going to be starting the derivative of the natural log. Now the derivative of the natural log is a very easy thing to do, but before we begin, we need to kind of go over some properties. Now the first three properties are what we call the expansion properties of logs. The first one, if I take the natural log of AB, I can split it. Natural log of A plus the natural log of B. Same thing, natural log of A over B becomes the natural log of A minus the natural log of B. And the natural log of A to the B becomes B natural log of A. And the last two are just some basic property that we should just know about natural logs. The natural log of E is 1, and the natural log of 1 is 0. And if you're looking for proofs of all of these, you can go back earlier into some of my other videos from pre-cal, and I do discuss those. Now, we do have to recall one more rule about natural logs, though, and that's the natural log of x. We have a domain restriction. X has to be greater than 0, always. Now, to define a natural log, and we always use ln. And people always say, Mr. Wernow, why do we use ln when defining natural log? And it's simple. It comes back to the day when I first started doing all this math stuff. It goes back, and all the books were written pretty much in French because they thought the French was the language of the intelligent people. So little did they know, right? So they said everything has to be in French. So natural log is log de naturel in French. I don't know if that's a true story or not, but it'd be kind of cool if it were. So to define a natural log, we define it as this. The natural log of x as the area. It's an area problem of 1 over t dt. So we define natural log as a differential. And this is kind of cool because it helps us to get the derivative. If I want to find the derivative of the natural log of x with respect to x, I take the derivative of the other side as well, 1 to x, 1 over t dt. And we should know how to do this. This is our second FTC. We get the derivative of the natural log of x being, take the derivative here, just replace the t with x, 1 over x. And there's our derivative. Now the official rule is this, because there's a chain rule on this. The derivative of the natural log of u with respect to x is the following. 1 over u du dx. It's our chain rule. Okay? And that's our rule. So let's take a look at a few examples of taking derivatives using natural log. Alright, question number 1. Ready? We want to find the derivative. Find dy dx. There we go. Scratch that out. Number 1. Let's let y equal the natural log of 2x. Now there are two ways I can do this, okay? There are two ways. Method 1. Okay, method 1 I don't like to use all that much, and we'll explain why later on. I get the natural log of 2x as my equation. I just take the derivative. 1 over 2x times 2. And that gives me y prime equals 1 over x. And there's our derivative right there. Okay? So can I pause this? No. So I'll be right back here to go over a couple more. Thank you. Have fun at the state show. Thank you, you too. We are back from our commercial break. So that's method 1. Now, method 2 is normally the method I like to use. Okay? And most people like to use as well. And that's this. If I have y equals the natural log of 2x, I can expand this. This becomes the natural log of 2 plus the natural log of x. So when I take the derivative, this becomes, well, the natural log of 2 is a constant, plus 1 over x. Now, I do get the same answer, as you notice, and it seems longer in this case, but we're going to do some really ugly ones in just a few moments. So you'll see why we like method 2. So let's try another example here. What if I gave you like kind of an easy one here? Y equals the natural log of x squared plus 1. Now I cannot expand this one, so I'm just going to go ahead and straight up take the derivative. Y prime equals, we get 1 over x squared plus 1. See, my rule says it's 1 over the inside. Okay? But now I got to take the derivative of the inside. That's my chain rule. And I multiply that by 2x. And I get 2x over x squared plus 1. And there's my derivative right there. Very easy to do. So let's take a look at one where we might have to apply a product rule. Let's take a look at number 3 right here. Whoops. Focus. Focus. Gosh darn it. No luck with technology today. So let's say we have y equals x times the natural log of x. Well, this is our product rule. Should look familiar to us. So when we take the derivative here, when we take our derivative, y prime, we're going to get the first times the derivative of the second. Remember, the natural log of x is 1 over x, plus the second natural log of x times the derivative of the first, which is just 1. And if I clean this up a little bit, we're going to get 1 plus the natural log of x. There's my derivative. Now, let's play around with this one for a little bit. Let's find the critical points. To find the critical points, we know set the derivative equal to 0. Set the derivative equal to 0. That's natural log there. So if I solve this, I get the natural log of x equals -1. Now, in order to solve this one, we have the inverse property, but I like to use a trick called what we call exponentiation. It's a cool verb to learn. And basically how it works is this. If I want to undo a natural log, I have to write this as an exponent because we know the following, that e to the natural log of x is x. So I am going to do that. I'm going to exponentiate the left side. And in doing so, I have to do the same to the right side. And we get x equals e to the -1 or 1 over e. But remember, we wanted the point, right? So now I have to find the value, f of 1 over e. I plug it into the original equation. I get 1 over e, natural log 1 over e. Well, that looks kind of weird, but if I write it this way, 1 over e times the natural log of e to the -1, we start to see something. I get 1 over e, and those cancel, -1. So my point becomes 1 over e, -1 over e. And there it is. Heck, if I wanted to, I can even determine if this is a maximum or a minimum value. And to do that, I use my sign test. F prime, F, here it is. Now, y at 0, remember the natural log has a domain restriction, we can't be 0. My one critical number, 1 over e. Now, I have to pick a number between 0 and 1 over e. Well, I don't know any. But I do know this. Anytime I'm in terms of natural log, I'm going to pick an x value in terms of e. So I'll pick -2, because that's -1. -2 is less than that. So this becomes then 1 plus, remember I'm plugging it into my derivative, 1 plus the natural log of e to the -2 just becomes -2. And I get a negative number, so it's going down. So what if I pick over here? Well, let's just do e to the 0. Let's just do e to the 0. Okay? So that's easy enough to do. Or I'm going to get 1 plus, well, the natural log of e to the 0 is just 0. That's positive. It goes up. So this is a minimum value right there. Very easy to do. And so you're going to see some stuff like that throughout the year. Let's take a look at number 4 here, but let's go back to doing some derivatives, what we came here for. Let's try something like this. F of x equals the natural log of the square root of x plus 1. Now, I could just take the derivative, but the easier way to do this one, again, use your expansion rules. So I'm going to write this as the natural log of x plus 1 to the 1/2. Expand it. I can drop my power. Interesting that log powers and derivatives for powers, polynomials have the same kind of rule. You can drop them. I wonder if there's a relationship there. I don't know. This becomes the 1/2 the natural log of x plus 1. Now, this is not the derivative. Not the derivative. Repeat, that is not the derivative. To take the derivative, I have to use my rule. I keep the 1/2. It's a constant. But the derivative of the natural log of x plus 1 is just 1 over x plus 1. And there's my answer. Very good. So let's take a look at another one here. Number 5 here. Number 5. Let's take a look at number 5 real quickly. El cinco. Number 5. Y equals. You know what? I heard you like natural logs, so I put a natural log inside your natural log. It's just natural as a log. I don't know why I put that there. That doesn't need to be there. So when I take the derivative, this is a chain rule right here. We're going to be using our chain rule. Remember what the chain rule says? Take the derivative of the outside times it by the derivative of the inside. So when I take my derivative, the derivative of the outside is the natural log of the natural log. So it's going to become 1 over the inside, the natural log of x, times the inside, well, the derivative natural log of x by itself is 1 over x. And there's our answer. So I could write this as 1 over x natural log of x. Or, if I'm going to be really brave, 1 over the natural log of x to the x. Do not try to take this derivative yet. We do not know how to take that derivative. Do not attempt that one just yet. Okay, I mean the antiderivative x to the x. That's a hard one. That's later. I like this. Keep it there. Keep it simple. All right, number 6. Well, let's take a look at a slightly more complicated one right now. What if we did something like y equals the natural log of x cubed? Again, this is another chain rule. Be careful, this is not the same as the natural log of x cubed. Here, only the x is being cubed. I can use my power rule. But over here, gosh darn it. But over here, the whole thing's being cubed. So I can't use my power rule. So when I take my derivative, we're going to get chain rule, take the derivative of the outside, 3 times the natural log of x squared times the derivative of the inside, 1 over x. And there's your derivative. So let's take a look at a trig one real quickly here, if they're not too hard. Number 7. What if we have something like y equals the natural log of the cosine of x? Now, people, why is this in parentheses? I mean, in absolute value? It's absolute value because cosine of x has negative values. And we can't have negative values underneath there. So when I take so I always have to put my trigs in absolute value symbols. We'll talk more about that when we talk about the antiderivative of them though. dy dx, chain rule, derivative of the outside, I get 1 over cosine of x times the derivative of the inside, negative sine of x. And if you notice, this is just the negative of the tangent of x. Now we've never taken, so now what that's going to allow us to do is take the antiderivative tangent of x. We're going to be able to do this rule now. We get negative natural log of the cosine of x plus something else. Cool. All right, one more example and then you're done. Let's take a look here at number 8. What about implicit differentiation? We always have to worry about those. So in implicit differentiation, what if we have something like, I don't know, let's make this one up. 3x plus 2 natural log of y minus y cubed equals 3. This is our implicit. This is our implicit. When we take the derivative, we get 3 plus, be careful, this becomes 2 times 1 over y dy dx. That's what this part becomes. Minus 3y squared dy dx, and don't forget that's 0. Any other time, remember I said, anything with the dy dx stays. So I'm going to go ahead and factor out my dy dx. That's going to give me 2 over y minus 3y squared, and that's going to equal, bring up the negative 3. So when I divide, we're going to get negative 3 over 2 over y minus 3y squared. And of course, remember, we are not done. I have to multiply top and bottom by y. And we get a final answer of negative 3y over 2 minus 3y cubed. And there's your derivative. Okay, so we've done all this. Now, I do have one more example. You can stop right now if you're good. But I'm going to take a look at a super duper hard one. Number 9. Okay? Why we like our expansion rules here, okay? So let's take a look here at number 9 here. What if I did something like this? Y equals the natural log of, let's say, the square root of x squared plus 1 over, let's say, sine of x. If I didn't do expansion rules, this would be really tough. So I'm going to expand this. And this would give me 1/2 the natural log of x squared plus 1 minus the natural log of the sine of x. Now we have to put these in brackets. We'll talk more about that later. So now I'm ready to take the derivative. By expanding it, it's going to make the derivative much easier to take. I expanded. Okay? That makes the derivative easy. This becomes 1 over 2 times 1 over x squared plus 1 times chain rule, don't forget your chain rule, 2x minus, over here, I get 1 over the sine of x, don't forget chain rule, the derivative of sine is cosine of x. And I can simplify this a little bit. The 2's will cancel, and I get x over x squared plus 1 minus, that's just the cotangent of x. So now we can start taking much more uglier derivatives. Alright, so have fun with these. Most people really tend to like them, and we'll see y'all later. Bye.